Good morning, students. This is Latif sir. Today in this video I will discuss about solid in liquid solution and their properties. Solid in liquid solution means uh, solid in liquid solution are those solution in which the solute is solid and the solvent is liquid. An example of such solution is salt water solution or glucose water solution. These solutions are solid in liquid solution. Okay. And these solutions have some important properties which are known as qualitative properties. Very important properties, qualitative properties. Okay, so you have to know what are these qualitative properties. Qualitative properties are those properties. Qualitative properties are those properties which depends only on the number of solid particles, which depends upon which depends only upon the number of solid particles in a solution irrespective of their nature. That is, these qualitative properties of a solution, especially for dilute solution in which a non-electrolytic non-volatile solute is present. Qualitative properties of such solution depends only on the number of solid particles, but does not depend on the nature of the solute. Okay, so solution containing non-volatile solute, especially non-volatile dilute solution containing non-volatile, non-electrolytic, non-associative, non-dissociative solute shows four different types of qualitative properties. So solution containing non-volatile, non-electrolyte, non-associative, non-dissociative solute, they shows four different types of qualitative properties, and these qualitative properties are relative lowering of vapor pressure, elevation in boiling point, depression in freezing point, and osmotic pressure. These are four important qualitative properties of dilute solution in which non-volatile solute is present. Okay, so first type of qualitative property is relative lowering of vapor pressure. Relative lowering of vapor pressure. You know, vapor pressure of a solution is vapor pressure of a solution containing non-volatile solute is always lower than the vapor pressure of pure solvent. In the previous video I have also told that the vapor pressure of a solution is always less than that of the vapor pressure of pure solvent. Okay, so if the vapor pressure of suppose you made a solution by mixing a solute B, solid solute B in a solvent, liquid solvent A, where B is solute and A is solvent, and B is solid in nature and A is liquid solvent. Okay, so if the vapor pressure of pure solvent is indicated by PA naught and vapor pressure of the solution is PA, then you know PA naught is always greater than PA, because vapor pressure of pure solvent is always greater than vapor pressure of the solution. And now see, lowering of vapor pressure after forming the solution by mixing a non-volatile solid solute in a liquid solvent, there will be a lowering in vapor pressure, a lowering of vapor pressure, and the lowering of vapor pressure is PA naught minus PA. This is the lowering of vapor pressure. Okay, where PA naught is vapor pressure of pure solvent and PA is the vapor pressure of solution. So PA naught minus PA is the lowering of vapor pressure of the solution. Now, what is relative lowering of vapor pressure? If you divide this lowering of vapor pressure, that is PA naught minus PA, if you divide this quantity PA naught minus PA by the vapor pressure of pure solvent, then you will get the term relative lowering of vapor pressure. If you divide the lowering in vapor pressure, that is PA naught minus PA, by the vapor pressure of pure solvent, that is Pa naught, then this term is known as relative lowering of vapor pressure. Okay, so relative lowering of vapor pressure is the ratio of lowering in vapor pressure to the vapor pressure of pure solvent. Relative lowering of vapor pressure is the ratio of lowering in vapor pressure to the vapor pressure of pure solvent. That is, relative lowering of vapor pressure means Pa naught minus Pa divided by Pa naught. And there is a Raoults law. There is a Raoults law related to relative lowering of vapor pressure, and according to this law, Raoults law of relative lowering of vapor pressure, the relative lowering of vapor pressure is equal to mole fraction of the solute in the solution, where Xb is the mole fraction of the solute in the solution. According to Raoults law of relative lowering of vapor pressure, the relative lowering in vapor pressure, that is Pa naught minus Pa divided by Pa naught, is equal to mole fraction of this solute in the solution, where Xb is the mole fraction of solute in the solution. Okay, so Pa you can write according to Raoults law, Pa naught minus Pa divided by Pa naught is equal to Xb. Okay, where Xb is the mole fraction of the solute in the solution. Okay, A represents solvent molecule and B represent solute molecule. And now you can write this equation also, because mole fraction means number of moles of B divided by total number of moles in the solution, that is Na plus Nb. Suppose in the solution Na mole solvent and Nb mole solute are present, then what is the mole fraction of solute? Mole fraction of solute will be mole number of solute divided by total number of moles in the solution, that is Nb by Na plus Nb. So you can write Pa naught minus Pa by Pa naught is equal to Nb by Na plus Nb, that is mole number of solute B divided by mole number of solvent A plus mole number of solute B. Okay, now for dilute solution you can assume that the mole number of solute in the solution is very less than mole number of solvent. For dilute solution you can assume that mole number of solute, non-volatile solute, is very less than that of mole number of pure solvent. Okay, so you can assume that Na greater than Nb for dilute solution. So you can write that Na plus Nb is almost equal to Na, because a value of Na is greater than Nb. Number of moles of solvent in the solution is very high than the number of moles of solute in the solution. So you can assume that Na plus Nb is almost equal to Na. That is, you can write Pa naught minus Pa by Pa naught is equal to Nb by Na. This is after taking the assumption that number of moles of solute in the solution is very less than that of solvent. Okay, so after taking this as assumption, you can write Pa naught minus Pa by Pa naught is equal to Nb by Na. Okay, and now you know number of moles means mass by molecular weight. Mass, which is represented by W, and molecular weight, which is represented by M. So Nb means Wb by Mb, capital Mb, and Na means Wa by capital Ma, where Wa is the weight of solvent in the solution and Ma is the molecular weight of the solvent, and Wb is the weight of solute in the solution, and Mb is the molecular weight of the solute in the solution. So after rearranging, you will get Pa naught minus Pa by Pa naught is equal to Wb by Mb divided by Wa by Ma, and after further rearrangement you will get this relation, that is Mb is equal to Wb by Wa into Ma into Pa naught divided by Pa naught minus Pa. That is, using this equation you can calculate the molecular weight of the solute in the solution, that is Mb. I have told that Mb is the molecular weight of solute. You can remember this equation or the last equation, any one equation you can remember. Okay, so using this equation you can calculate the molecular weight of the solute in the solution. Okay, there are some numerical problem you have to solve based on this uh, on this formula. Okay, that is based on relative lowering of vapor pressure. So remember this formula. And now see next type of qualitative property, elevation in boiling point, which is represented by delta TB. Elevation in boiling point. So first you have to know what is the boiling point. Boiling point of a liquid is the temperature at which its vapor pressure become equal to the atmospheric pressure. Boiling point is the of a liquid is the temperature at which its vapor pressure become equal to the atmospheric pressure. Okay, and you know vapor pressure of a solution is containing non-volatile solute is always lower than that of pure solvent. As the vapor pressure is decreases after forming the solution in which non-volatile solid solutes are present, the boiling point of the solution will be higher. This is because of lowering of vapor pressure of the solution. Okay, so as the vapor pressure of a solution containing non-volatile solute lower than that of pure solvent, its boiling point will be higher than that of pure solvent. So here this term elevation in boiling point, uh, it is used, this term is used because the boiling point of the solution will be higher than that of pure solvent. Okay, suppose boiling point of pure solvent is TB and boiling point of the solution is TB dash, and I have told that the boiling point of the solution will be higher than boiling point of solvent. So elevation in boiling point, which is written as delta TB is TB dash or TB prime minus TB. This is the elevation in boiling point. Okay, and graphically it is showing that how the vapor pressure of solution changes with temperature. If you increase temperature, you will see that vapor pressure of pure solvent and vapor pressure of solution both will increase. Okay, if you increase temperature, you will see that vapor pressure of pure solvent and vapor pressure of solution both will increase. Okay, and solution will boil only when the vapor pressure of both solution and solvent will be equal to atmospheric pressure, that is 1 atm. So vapor pressure of solvent become 1 atm. You can see according to this figure, vapor pressure of solvent, pure solvent, become 1 atm when temperature is TB, and vapor pressure of the solution become equal to 1 atm at temperature TB prime. Okay, so from this diagram it is clear that vapor pressure of the solution from this diagram it is clear that boiling point of this solution is higher than that of pure solvent, that is TB dash is greater than TB. Okay, and there is a Raoults law related to elevation of boiling point, and according to Raoults law of elevation of boiling point, the elevation of boiling point is proportional to molar concentration of the solution. According to Raoults law of elevation of boiling point, the elevation of boiling point is directly proportional to the molar concentration. It is molar concentration of the solution. That is, delta TB is proportional to M, or you can also write delta TB is equal to Kb into M, where M is the molality, molar concentration of the solution. Okay, and now you know how to calculate molality of solution. Molality, the formula of calculation of molality of solution is molality, which is represented by small m. Molality of the solution is equal to Wb by Wa into 1000 divided by Mb, where Wb is the Wb is the weight of solute, Wa is the weight of solvent, and Mb is the weight of molecular weight of solute. Okay, suppose you have dissolved Wb gram solid solute, non-volatile solute in Wa gram solvent, and molecular weight of the solute is Mb. Then the formula of calculation of molality is equal to Wb by Wa into 1000 by Mb. Just put this value and the equation becomes delta Tb, that is elevation of boiling point, is equal to Kb into Wb into 1000 by Wa into Mb. Remember this equation. Using this equation, this equation, you have to solve some numerical problem based on based on elevation of boiling point of a solute containing non-volatile solute, solid solute. Okay, and here the proportionality constant is Kb, taken as Kb. Kb means molar elevation constant or ebullioscopic constant, which depends on the nature of this Kb constant, which depends on the nature of solvent. Okay, for different solvent the value of Kb is different. And how to define the molar elevation constant or ebullioscopic constant? If the molality of the solution is 1, if you made 1 molar solution, then the elevation of boiling point is will be equal to Kb. If the value of M is 1, if you make 1 molar solution, then the elevation of boiling point of that solution will be equal to molar elevation constant, that is delta Tb will be equal to Kb when M is equal to 1, if the molality of the solution. Okay, for different solvent the value of Kb is different, and using this relation delta Tb is equal to Kb into Wb into 1000 by Wa into Mb, you have to calculate some numerical problem. You have to solve some numerical problem in which you have to calculate the mass of either the molecular weight of solute, that is Mb, or weight of solute in the solution. Okay, and sometimes you have to calculate the elevation in boiling point, or final, what will be the final boiling point. Delta Tb means you can also write instead of delta Tb you can also write Tb prime minus Tb is equal to Kb into Wb 1000 divided by Wa into Mb. Okay, and unit of Kb, molar elevation constant, is kg mole Kelvin kg per mole. Unit of Kb is Kelvin kg per mole. Okay, and here it is written what is Wa. W is mass of solvent, Wb mass of solute, Mb molecular weight of solute. Now see, next qualitative properties is depression in freezing point. This is the third qualitative property. Like elevation in boiling point, solution containing non-volatile solid solute in a solvent in a solution, the freezing point of the solution will be lower than the pure solvent. This is known as depression in freezing point. Okay, boiling point of such type of solution will be higher than pure solvent, but freezing point will be lower than pure solvent. Okay, so freezing point of of a liquid is the temperature at which the vapor pressure of the solvent in its liquid and solid phase become equal. As a liquid, the freezing point of a liquid is the temperature at which vapor pressure of the liquid become equal to vapor pressure of the solid. Graphically, you can see from this diagram, this is the vapor pressure versus temperature graph. Okay, a liquid will freeze only when the vapor pressure of the pure liquid will become equal to vapor pressure of solid. This is for solid state, and this line is for pure liquid, and this represent change in vapor pressure of solution. Okay, if you decrease temperature, then vapor pressure of the liquid, pure liquid, and vapor pressure of solution, pure liquid means pure solvent. Okay, vapor pressure of both pure liquid and pure solvent will be decreased if you decrease temperature. Okay, and when the vapor pressure of pure liquid will become equal to vapor pressure of solid, then the liquid will freeze, and this temperature is known as freezing point of the liquid. And according to this diagram, freezing point of the pure liquid is Tf, which is represented by Tf, and freezing point of the solution is Tf prime, and you can see Tf prime is less than Tf. Vapor pressure freezing point of the solution is lower than freezing point of pure solvent, so there is a decrease in freezing point. freezing point of Freezing point of solution is lower than freezing point of pure solvent, so there is a decrease in freezing point, and decrease in freezing point, which is represented by delta Tf, is equal to Tf prime minus Tf. This difference is known as depression in freezing point of the solution. Okay, so as we know, vapor pressure of solution containing non-volatile solute is lower than that of pure solvent. Solid form solid form gets separated solid form gets separated out at a lower temperature. That is, the freezing point of the solution will be lower than that of pure solvent. Suppose the freezing point of the solution is Tf prime and freezing point of the pure solvent is Tf, then depression in freezing point is Tf prime minus Tf. Okay, and there is a Raoults law of depression of freezing point, like Raoults law of elevation of boiling point. It is similar. Depression of freezing point of the solution in which non-volatile solute is present is directly proportional to molar concentration of the solution. Similar statement like elevation of boiling point in depression of freezing point also, according to Raoults law, you can say depression of freezing point of this solution is directly proportional to the molar concentration of the solution, that is delta Tf proportional to m, small m, where small m is the molarity of the solution. Or you can also write delta Tf is equal to Kf into m, where Kf is a constant, proportionality constant, and here that Kf term Kf is related to depression of freezing point. So Kf is known as molar depression constant or cryoscopic constant. Okay, and its unit is Kelvin kg per mole, and we know the formula of calculation of molality means mass of solute into 1000 divided by mass of solvent into molecular weight of solvent. This is the formula of calculation of molality. So put the value of molality, that is delta Tf, will become delta Tf is equal to Kf into Wb into 1000 by Wa into Mb. Okay, remember this equation, or after further rearrangement you will get Mb, that is molecular weight of solute B, is equal to Kf into Wb into 1000 by Wa into delta Tf. Okay, in the previous case, that is elevation of boiling point, I have told what is Wb, what is Wa. Okay, where Wa is the weight of or mass of solvent, Wb is the mass of solute, Ma is the molecular weight of solvent, Mb is the molecular weight of solute. Okay, you have to remember these terms. So based on this equation you have to solve some numerical problem, that is you have to calculate molecular weight of solute, or you have to calculate the depression in freezing point, or you have to calculate what will be the final freezing point, okay, of the solution. The value of mass of solute, mass of solvent, this value will be given. Okay, value of Kf is molar depression constant or cryoscopic constant. It also depends on the nature of solvent only. For different solvent the value of Kf is different. Okay, and last type of qualitative property is osmotic pressure. Osmotic pressure, which is represented by pi. First you have to know what is osmosis. Suppose you have separated two solution of different concentration, or you have separated a pure solvent from a solution by a semi-permeable membrane. Permeable membrane, then you will see the phenomena osmosis. What you will see, the solvent molecule will pass through the semi-permeable membrane from pure solvent to solution side, or from dilute solution to concentrated solution. Only solute particles, solvent particles will pass, not the solute particles, because semi-permeable membrane allows the passing of solvent particles only, not solute particles. Okay, and this is known as osmosis. So osmosis is the phenomena of spontaneous flow of solvent molecule. Osmosis is the phenomena of spontaneous flow of solvent molecules through a semi-permeable membrane from pure solvent to pure solvent to solution, or from dilute solution to concentrated solution. And this phenomenon is known as osmosis. Okay, and there some example of semi-permeable membrane is given here. Okay, semi-permeable membrane are those membrane which allows the passing of solvent molecule only, not the solute molecule. Okay, so natural semi-permeable membrane is animal bladder or cell membrane, and there are some artificial semi-permeable membranes such as copper ferrocyanide. Okay, Cu2 FeCN6 is an artificial semi-permeable membrane which does not uh, in non-aqueous solution as it dissolve in them. Okay, now what is osmotic pressure? You know, the vapor pressure of pure solvent is always higher than the vapor pressure of solution. That's why the solvent molecule will pass from the solvent molecules are passing from solvent to pure solvent to solution side. This is because the vapor pressure above the pure solvent is higher than the vapor pressure of above the solution. Okay, this is the cause of osmosis, the difference in vapor pressure of pure solution as pure solvent and solution. Okay, and now if you want to stop the process of osmosis, you have to apply extra pressure just above the solution side. Okay, so osmotic pressure of a solution is the excess pressure that must be applied to a solution to prevent osmosis. You have to apply the excess some excess pressure to stop the osmosis, that is flow of solvent molecule from solvent to pure solvent to solution side through semipermeable membrane. If you want to stop this process, you have to apply some extra pressure just above the solution side. Okay, and this extra pressure is known as osmotic pressure. So osmotic pressure of a solution is the excess pressure that must be applied to a solvent to prevent osmosis. Okay, and there is a formula of calculation of osmotic pressure, and it has been found that experimentally that osmotic pressure is proportional to molarity of the solution. Osmotic pressure, which is represented by by pi, according to experimentally it is found that this pi osmotic pressure is proportional to molar concentration. It is not molal, it is molar concentration of the solution, that is molarity of the solution at a given temperature, and it is also proportional to temperature. Okay, so pi is proportional to C, and pi is osmotic pressure of the solution is proportional to temperature. Okay, so you can write by combining this equation, pi is proportional to C and T, and if you want to omit the proportionality sign, then you can write pi is equal to some constant which is taken as R, some constant into Ct, that is pi is equal to CRT, and where R is the universal gas constant. Okay, so the osmotic pressure formula of calculation of osmotic pressure, pi is equal to CRT, that is pi is directly proportional to molar concentration, that is molarity of the solution, and pi is directly proportional to absolute temperature, and R is the universal gas constant. Or you can also write pi is equal to N by V RT, where N is the number of mole of solute. If N2 moles N mole solute is present in V liter solution, if N mole solute is present in V liter solution, then molarity of the solution is C is equal to N by V. Suppose N mole solute is present in V liter solution, then molarity of solution will be equal to C is equal to N by V. So you can write pi is equal to N by V RT, where N is the number of moles of solute. Okay, so after rearranging, you can write pi V. Now put the value of mole number of solute. Mole number of solute will be equal to, that is here it is mole number of solute is taken as N2. Okay, so if mole number of solute is N2, then N2 will be equal to mass of solute divided by molecular weight of solute. Here solute is taken as 2, or you can write as B, NB, that is WB by MB. Okay, so pi V is equal to W2 by M2 RT, or M2, that is molecular weight or molecular mass of solute, is equal to W2 RT by pi V, where W2 is the mass of solute. Okay, so this is the main equation of osmotic pressure calculation, pi is equal to CRT. And after rearranging this equation, you can get this equation, M2 is equal to W2 RT by pi into V, where M2 is the molecular weight of the solute, and W2 is the mass of the solute, R is universal gas constant, T is temperature in Kelvin scale, pi is osmotic pressure, and unit of osmotic pressure is atm, and V is the volume of the solution. Okay, now based on the basis of osmotic pressure, solution can be three types. One is hypertonic solution, another is hypotonic solution, and the last one is isotonic solution. Hypertonic solution, a solution is called hypertonic if its osmotic pressure is higher than that of the solution from which it is separated by semipermeable membrane. A solution is called hypertonic solution if its osmotic pressure is higher than that of the solution from which it is separated by a semipermeable membrane. Okay, and hypotonic solution hypertonic solution, a solution is hypotonic if its osmotic pressure is lower than that of the solution from which it is separated by a semi-permeable membrane. An isotonic solution means if two solution and the two solution if osmotic pressure of two solution are equal, then both the solution are called isotonic to each other. Okay, so two solution are called isotonic if they exert the same osmotic pressure and this solution have same molar concentration. Okay, so if osmotic pressure of a solution is greater than osmotic pressure of other solution, then the previous solution is known as hypertonic and this solution, the second solution, will be known as hypotonic. And if the osmotic pressure of both the solution become equal, then both the solution are isotonic to each other. Okay, and now see the reverse osmosis, just opposite of osmosis. Reverse osmosis, when the external pressure applied on the solution is more than osmotic pressure of this osmotic pressure, the solvent flows from the solution to pure solvent, just opposite, in opposite direction, and this is known as reverse osmosis, when the external pressure applied on the solution is more than osmotic pressure of the solution, the solvent flows from this solution to this pure solvent, that is in opposite direction of osmosis, and this is known as reverse osmosis. And desalination of seawater is done by reverse osmosis. Okay, this is the application of reverse osmosis, and in next class I will discuss about abnormal molar masses. Thank you, students.